Hi everyone. So today we are going to discuss about photodetectors. In the last class, we had discussed about optical sources, namely light emitting diode and laser. So today we are going to discuss about photodetectors. So what are the requirements of a photodetector? The first, what does actually, let us first understand what does a photodetector do. So it basically converts the light uh, power or optical power into electrical energy. That's a basic function of photodetector. So what we require in a photodetector, the size should be small, because if you want to mount this maybe on your mobile phone or want to use in your, as an attachment to your uh, laptop, you require that the size of the photodetector should be very small. So first requirement, that the size of the photodetector should be very small. And it should have high conversion efficiency, meaning whatever light is falling onto it, most of it should be converted into electrical signal, which we are going to process. It should have high sensitivity at the operating wavelength. So suppose in a telecommunication scenario, you are working at either 850 nanometer or 1310 nanometers or 1550 nanometers. The kind of detector you should use, that it should give you high sensitivity at that particular operating wavelength. If you are using this in a visible light scenario, for example, so it will give you a high sensitivity against visible light. So it should have, depending upon the application, it should have high sensitivity at the operating wavelength. High response speed, which means the photodetector should be able to respond at high bandwidth, because in a typical optical communication system, whether it is wired or wireless using optical fiber or wireless, you have a transmitter and you have channel here and you have receiver here, right? So this transmitter is basically combination of either LED or laser, and then receiver is actually converting optical signal, whatever is coming through the channel, to electrical signal. Now the goal is to transmit very high speed from optical transmitter to optical receiver. It could be of the order of, say, gigabits per second. So what we want, that the Rx, in this case photodetector, which we also call as PD, should respond at this rate. So it should have a high response speed. So we'll study in detail about the requirements, how one can improve the response speed. And photodetector generates noise. Those sources of noise or the noise generated inside the photodetector we will study, and the idea is to have minimum noise, so that at the receiver your signal to noise ratio is maximized. So what is the basic principle of photodiode? So it is based on a process called absorption. Remember, in LED case we had studied about absorption, spontaneous emission and stimulated emission. So what happens when a light falls onto a semiconductor? The photon energy which is there in the light is absorbed. It generates electron hole pairs, and this device is biased. It is normally reverse biased. And those electron hole pairs are actually under the influence of this bias, they are swept away or they drift, and in the process they generate current which can be collected through which can be, you can have a RL and the voltage can be developed across RL. So you get light, the current or the voltage across RL proportional to the intensity of the light. So that is a basic principle of photodiode. So you require what kind of wavelength you require, because the photon which has energy greater than the band gap of the p-n junction, only then it will be absorbed and convert into electron hole pairs. So you require a certain wavelength which will be your wavelength will be sensitive to wavelength which is less than this lambda c, lambda cutoff. So this lambda cutoff is defined as SC divided by EG. This is not subscript, this is h Planck's constant and c is velocity of light. EG is the band gap of the photodiode junction. So in terms of you can put the values of Planck's constant and velocity of light, then this is approximately equal to 1.24 divided by EG. EG is the band gap energy and it is in electron volts. So this is the lambda C or the lambda cutoff for different material. For silicon, the EG is 1.11, the corresponding lambda C is 1.13. So it is generally sensitive at wavelength less than 1.13 micrometer. So for example, if you are using 850 nanometer transmission, so this can be a good choice. For germanium, the band gap energy is 0.67. The corresponding cutoff wavelength lambda C is 1.85. So this could be a good candidate for 1550 nanometer transmission. The third one is gallium arsenide. The band gap is 1.43. The corresponding cutoff wavelength is 0.87. And in gas is 0.75 and the corresponding cutoff wavelength is 1.65. So let us now understand the specific diode which is used for in optical communication system, whether it is fiber based or optical wireless system. So let us first understand the structure. The structure is actually, there is it's a p-n diode, and there is a intrinsic region in between, which I am denoting this as I. So this I is actually, this intrinsic region is actually kept wide. I'll tell you why it is kept wide. Intrinsic. It is kept wide and this is lightly doped. So there are no free electron hole pair inside the I region. So the impedance of this I region is very, very high. So the voltage basically is across the I region. And this PIN photodiode is actually reverse biased. This is in contrast to LED, which was forward biased, and that was a PN junction. So when optical energy falls, it is absorbed and it generates electron hole pairs. So I'm denoting this hole as a hole and this is say electron as a dot. So, and because the voltage is across the I region, they are drifted away, and in fact I should make a little, change the diagram little to include resistor. So this is output and this is resistor. The current So this electron will go, hole will go in this direction, electron will go in this direction. And under this influence of reverse bias, there is a drift current which flows across this device, and this passes through a load resistor, which is RL, and you get a voltage across RL. This is the bias part. Let me denote this as a VB. So this is a basic structure of PIN diode, and it is kept wide, the I region, because we want that photon should have maximum chance of getting absorbed inside the intrinsic region, hence producing electron hole pairs. If it is narrow, probably the probability that it generates electron hole pairs is less. So that is why it is kept high. So this is a structure of PIN photodiode. There are some quantities which define the property of a photodiode. So one of them is responsivity, which is defined as the photocurrent divided by the optical power. So this optical power, let us say this is P0, and the current is I0 here. So basically, how much photocurrent is produced when you launched optical power P0. So that ratio is called as a responsivity. So this is generally denoted by R. The other quantity which is important is quantum efficiency. Quantum efficiency is when the photon strikes the PIN junction, electron hole pairs are generated. It is not necessary that all photon will generate electron hole pairs. Some may be, there may be some recombination, or they may be lost. So not every photon will result into electron hole pairs. So basically the ratio of number of electron hole pairs generated divided by number of incident photon, that tells you the quantum efficiency of the photodiode. So this is defined as neta, quantum efficiency. So now let us try to understand and find out mathematical expression for responsivity and quantum efficiency. So inside a semiconductor, if I launch power P0, it is absorbed as the power travels through the semiconductor diode. This could be, for example, W. Then the power falls because it is getting absorbed. So as it travels, it falls. And this can be represented by, this is function of Z here. Pz, power at point Z, some point Z, is equal to P0. P0 is the incident power into 1 minus E alpha function of lambda, this function of lambda, into Z, the distance. And alpha is the absorption coefficient, which is actually function of wavelength. So this is the power at some point inside the semiconductor. What happens actually that when the power P0 gets is incident on the PN junction or PIN photodiode, then not whole part goes inside the device. Some part is getting reflected. Some part gets reflected back. So let us define that part as the one which is reflected is defined by the reflection coefficient of the device. So effectively the power which goes inside the photodiode is P0 into 1 minus R into 1 minus E alpha, which is a function of lambda, into the width. This is the power you get after traveling a distance of W. So the number of photons per unit time can be found out. This is the power. So number of photons will be, you have to divide this power by h nu. you will get number of photons. So this is a number of photons per unit time. So this expression has been divided by h nu. So this becomes P0 into h nu, 1 minus r. This is because of the reflection, and 1 minus e raised to power alpha. Now I am not writing this function of lambda. This is understood, or otherwise unnecessarily may create some confusion. But this alpha is the absorption coefficient, is function of wavelength into the width. And the photocurrent, because the number of photons absorbed per unit time are this, and the photocurrent I will be, you have to multiply this by E by h nu into 1 minus r, 1 minus E alpha into that P0. This is the incident power, P0 is incident. And this factor is actually takes care of the fact that not all photons will result into electron-hole pairs. So this factor basically tells you what proportion of photon is converted into electron-hole pairs. So generally this epsilon should be 1 ideally. All the photons should result into electron-hole pairs, but in practice doesn't happen that way. So this epsilon will be less than 1. So you have to multiply in order to get the photocurrent which flows through the resistor or the load is a function of this epsilon. So as we defined the efficiency earlier, which is neta, that is the number of electron-hole pairs divided by the number of incident photons. So these are the number of electron-hole pairs, I divided by E, and number of incident photons is the power incident on the photodiode divided by h nu. So I put the values which I had done calculated last in the earlier discussion. So this will become 1 minus r into 1 minus e raised to alpha w into epsilon. And if I define the responsivity, it is defined as photocurrent divided by the optical powers. The units of responsivity, by the way, is amperes per watt. How many amperes you generate when you give 1 watt of power? So generally in optical communication, you don't generate amperes or watts of power. Generally you have milliamperes of current and the power is milliwatt. But this R or the responsivity is generally, represented as amperes per watt. So photocurrent divided by optical power. Photocurrent generated was I naught, optical power P naught, and just manipulating the earlier equations, we get responsivity as efficiency into E by h nu. So we got expression for efficiency and we got expression for responsivity, which can be further simplified here as E epsilon into h nu 1 minus r 1 minus e raised to alpha w, and we can also equivalent write in an alternate fashion. The responsivity is lambda divided by 1.24 into efficiency, where lambda is in micrometers. So while calculating the responsivity using this equation, you have to put lambda in micrometers, and efficiency anyway is dimensionless quantity. So lambda divided by 1.24 into efficiency will give you the responsivity. So an example, just to give you some feel of the values, if I'm operating at lambda is equal to 0.8 micrometer or 800 nanometers, and the absorption coefficient is 10 raised to minus 5 per meter or meter inverse, and I'm using silicon as a semiconductor material, the refractive index is 3.5, and the depletion layer width, which is the W in my case, is 20 micrometer. And I assume that sigma, that epsilon is 1, where the conversion of all the photons will result into electron-hole pairs. And R can be calculated into N1 minus N2 divided by N1 plus N2 whole square, where N1 is refractive index, N1 at the interface. Assuming the N1 is air and N2 is 3.5, so you get R as 0.31, and so we can calculate the value of efficiency and responsivity if you are given these parameters. So in this case, if you plug in the values here, you get a efficiency of 0.6 or 60%, and responsivity you get 0.39 amperes per watt. So each 1 milliwatt power which is incident on the photodiode will generate about 0.39 milliamperes of current. So these are the efficiency and responsivity values for this particular example. Another important thing which we'll use quite frequently while finding out the power the power collected by the photodiode is field of view. So each photodiode has certain field of view. The light falling in this cone, this is actually a solid angle, so you have to visualize this in 3 dimensions, will get absorbed and will get converted into electrical current. So this cone or this solid angle is referred as a field of view. So you can make the field of view very narrow, you can make it wide if you want to collect light from all possible angles, and if it is a point-to-point transmission, you will try to make it narrow. So this field of view is very important when you're designing an optical wireless communication system. So now let us understand the role of RL, the load resistor, which we had discussed when we were discussing about the PIN diode. So again, I'll redraw this picture of PIN diode. So this is P, this is my I region, this is N region, and this is reverse biased. And there's a resistor here. The current flows, and let us denote this as RL. And again, there are hole and electron. They are generated as a result of incident photon energy, and this hole will move in this direction. It will be swept away in this direction, and this electron will be swept away in this direction. So what value of RL you should select? So let us understand this RL here. So initially, when there is no current or no photon energy flowing, the whole bias voltage VB, let us say, is across the I region. And when the photon energy is incident on this PIN diode, it will result into some current, and then there will be a voltage across RL, and that voltage is actually VRL is equal to responsivity of the photodiode into P0, the power incident, which is actually current, because I is equal to R over P0, or responsivity is responsivity, I should write the current is actually equal to responsivity over P0, because we know we had defined responsivity as the current, photocurrent divided by the power incident. So this is I into RL. So this is the VRL, which is across the load resistor. So what is the maximum value it can have? The maximum value it can have is VB, which is the bias. This can be written as capital B. And this is equivalent to R, responsivity, into P max. So that is the maximum power. Because if you incident more power than this, you will not get any additional current. It will get saturated. So that is the maximum power you can give to the device into RL. So that is the maximum value of VB. So P max of a photodiode, which actually tells you the range in which the photodiode will respond in terms of power. So P max will be VB. I mean, it's better to change at one place. So this is VB. So let me write this as BVB. P max will be VB by responsivity into RL. Now, if RL decreases, if I reduce the value of RL, this P max will increase, which means my detection range is increased. I am able to detect, wide value of power because this P max has increased. All right. On the other hand, if I see the sensitivity, that is the ratio of the voltage which is developed across RL divided by the incident power, is given as responsivity into RL. So this is the sensitivity part. So if I decrease RL, this sensitivity also decreases. So by decreasing RL, I was able to increase the P max, the detection range, but at the same time, I have compromised on the sensitivity. So you have to decide the value of RL depending upon whether you want a good detection range or you want good sensitivity. So let us see this with an example. If the responsivity is 0.5 amperes per watt, and let us initially have RL as 100 ohms, then the P max, if RL is 100 ohms, is actually 40 milliwatts. If you give power more than 40 milliwatts, it will get saturated. It will not respond. So P max is 40 milliwatt. And if you see the sensitivity, it is 50 millivolt per milliwatt. Now let us see when I increase this RL, what happens to these values. So I have increased the RL to 10 kilo ohms. And if I calculate P max, this is 4 milliwatt. My detection range has decreased. Whereas if I see the sensitivity part, it becomes 5 volt per milliwatt. That means my sensitivity has increased. I am able to get 5 volts per milliwatt, which was earlier 50 milliwatts per milliwatt. This is 5 volts per milliwatt. So earlier was 50 millivolts per watt. So depending upon your sensitivity or the detection range, you select the value of RL. So RL plays a very important role in the design of a receiver based on photodiode. Now let us understand the response time. So response time understanding, again we'll have to draw our PN structure, sorry. So let me again redraw and then we will discuss about the response time. So this is P, this is N. This is reverse biased, and then you have the RL here, and these are the where you draw the voltage. Now this is P region, this is I. So there are holes and there are electrons which are generated as a result of this incident light of power, say P0. And hole will move in this direction and I will move in this direction. All right. So if these electron hole pairs are generated in this region, it is called diffusion. So this process is called diffusion. And it's a slow process, so electron hole pairs will take some time to generate current. If that happens in this region where there is a voltage, so this electron hole pairs, they are swept away and they generate current, and this is called as drift current. So you have two parts. One is drift current and the diffusion current. So we want actually this P and N to be very, very small so that the diffusion component is much less, so that we will see that it will not degrade your response time. So what I want that all the photon electron pairs, electron hole pairs should be generated within the I region, and they are drifted with a drift velocity, and the delay component is much less and the response time of the device is very high. So I can call this as here hole diffusion. This will be hole diffusion, and this is electron diffusion. And let us see the length of this device is, or the I region is L, where I want the whole activity happening in this L region. So when electron actually when is swept towards the which constitute the current because of the drift, it will attain some velocity which is called as the saturation velocity. Let me define that as VSC. So that electron pulse which will generate will be something like this. So this will be L over VSC. And similarly, the hole will contribute to the current, and that will attain some velocity VSH, and we know the ratio of VSC and the VSH, the saturation hole velocity, is approximately 4. So this will generate into a current pulse which will be little wider, and this will be L divided by VSH. So this is how it will be generated, electron current pulse. So let me denote this as electron current pulse, electron current pulse. And this is hole current pulse, hole current. So if these electron hole pairs are generated in the middle, each one will travel L by 2 distance. But in actual practice, electron hole pairs can be generated anywhere inside the I region. So effective pulse which you launch here, if you see the electron current pulse because of the optical pulse which is launched in this fashion, then it will be a little distorted. So this will be something like this. And similarly, the whole pulse, because it is generated throughout the eye region, and if you take the sort of average of it, it will be something like this. So this is the corresponding whole current pulse, and this is the electron pulse. And because both are contributing to the current, so this pulse which was launched like this, and if you add them up and including the diffusion part, then what you get is not this kind of pulse, but you get a distorted pulse. So because of the diffusion, the drift nature of this device, your pulse gets distorted, and this is what you get at the output, right? So this is going to limit your response time, because if the distortion is too much, then there may be interference with the next pulse and the response time gets reduced. So if I see the current which is generated when the light falls from the P side is n number of electrons into E divided by the transit time, the time it takes to travel the device, which for electron is n into E. T transit is VSC divided by L. And if the light is from the N side, then the current which is generated gives you n into E VSH. This is the saturation velocity of the hole, VSH. This is the saturation velocity of the electron, is NE VSH divided by L. So this will result, as I explained you, the distortion of the input pulse, which I had discussed here. The input pulse gets distorted because of this diffusion and the drift phenomena, which I have explained in detail here. So now let us try to calculate the response time. What is the maximum bandwidth I can achieve in a photodiode? And if I want to improve, what are the ways of improving it? So let us try to do some calculations to understand the response time. So let us assume that the photon flux which is incident on the PIN diode is, say, phi t, which is some sinusoidal or some modulated signal, which is given as phi 0 into 1 plus m sin omega t. M is the frequency and m is the modulation index. This is the photon flux which is incident on the photodiode. Now let us try to understand. Let me break this photodiode into a smaller structure, which is something like this. So this will be, width is this thing, and let me take a slice here, which I call as delta x. So let me see what is the carrier, number of carrier which are passing through this small portion delta x, and then we will try to integrate this from 0 to whatever the length is. Suppose the length is L up to L, right? And then find out the total carrier which are generated. So if I want to calculate the carrier passing through this delta x, which is a thin slice here of width delta x, this is given by N0. N0 is the initial number of electron carriers generated into 1 plus m sine omega t, and this t minus x divided by velocity, saturation velocity of the electron is what all electrons which are generated prior to this will actually contribute to the electrons which are passing through this thin slice, which is delta x. So the electron which are generated in this region will contribute the number of electrons passing through this delta x. So this is represented as n0 into 1 plus m. M is a modulation index, sine omega t minus x by VSE, saturation velocity, into dt. The total carrier in the transit will have to integrate from 0 to L. So this I am integrating from 0 to L into n0 divided by saturation velocity into 1 plus m sine omega t t minus x VSE into dx.